One of the goals I have for the Raised Beaches podcast is to introduce scientific papers that I personally find interesting. And they'll always have a paleoclimate focus, but maybe they'll be biased to the things that I research. And today I'm only going to introduce one paper because this podcast is already running quite long. And this paper is based on a presentation that I saw at the Japan Geoscience Union conference that I was talking about earlier. And it's by Sun-Ming Hu and et al. And its title is Sustained North Atlantic Warming Drove Anomalously Intense MIS-11C Interglacial. And this was published recently in Nature Communications. So the first question you probably have is, what is MIS-11C? And if you are into paleoclimate, MIS is of something that you'll become very familiar with, and it stands for Marine Isotope Stage. So in paleoclimate, we divide time periods into these so-called isotope stages, and they're derived from oxygen isotope variations in the oceans, which are measured from these single-celled organisms called foraminifera. And I'll do a more detailed discussion of this in a future episode, but the important thing is that there are two major isotopes of oxygen. One has oxygen 18, which has 10 neutrons, and oxygen 16, which has 8 neutrons. And because oxygen 18 is slightly heavier than oxygen 16, when there's evaporation coming out of the ocean, oxygen 16 will preferentially be taken out, and when the ice sheet builds up, that means in the ocean, oxygen 18 will increase. And Marine Isotope Stage 11C is a period between 396 and 426,000 years ago. And there's been measurements of these oxygen isotopes for since the Pliocene, about 5 million years ago. And basically, there's these rhythmic changes in the oxygen 18 to oxygen 16 ratio. So this corresponds to times when the ice sheets expanded and shrank in the northern hemisphere. So what's special about Marine Isotope Stage 11C is that it is the longest and most intense interglacial in the past 3 million years during the Quaternary. And however, the issue is that the changes in these oxygen isotopes, the buildup and the shrinking of the ice sheets follow what is known as Milankovitch orbital theory. And in essence, what that is that because of the gravitational attraction of the planets, the Earth's axis of rotation will slowly change relative to the plane of the Earth's orbit. And during the times when the Earth's axis of rotation is pointed towards the sun in a more direct way during the northern hemisphere summer, you'll have what is known as an interglacial period where the ice sheets will shrink. And when it's pointed away, the ice sheets will grow. So Marine Isotope Stage 11 doesn't follow that so well because the intensity of the northern hemisphere summers during this period was not particularly large compared to other interglacials, including the Holocene, the current interglacial. So with that context, Hu et al. measured a climate record from a rock known as a flowstone. So a flowstone is a type of speleothem, a cave rock. So in a cave, you'll have water dripping down from the top of the cave, and the water will contain a certain amount of calcium, and that calcium will precipitate out of the water and form a mineral called calcite. And over time, these rocks, like a flowstone, will slowly grow. And basically, what you can do is you can take a slice or a drill through the flowstone, and you measure the chemistry of the rock over time, and that gives you an understanding of the conditions of the water. And the water chemistry will change based on what the climate is. So, for instance, if you have warmer temperatures or water precipitation sources changing, or if it's drier, or if it's wetter. So these things affect the chemistry of the water that's dripping down to form these flowstones. So this flowstone record comes from a cave in northern Italy called the Bassora Cave, and the chemistry in the flowstone should reflect changes to the climate in the northeastern Atlantic and the Mediterranean. And their hope is to link this record to marine isotope records, which stretch for a much longer period of time. And the marine isotope records are not very well defined in terms of chronology, but with a speleothem, in this case a flowstone, it's possible to get a really precise age on the chemistry record, because you can use uranium-thorium dating. So uranium gets incorporated into the calcite of the flowstone, and uranium, it's radioactive, so over time it converts to thorium. And based on the amount of thorium relative to uranium, you can tell what the age is. And this is what they did. They collected a lot of uranium-thorium dates to find the precise age of the flowstone record. And there was a few things that they measured. The first is the strontium and calcium ratio, and carbon isotopes, so the ratio of the carbon isotope 13 and the carbon isotope 12. And these records give an indication of how dry and cold it is above the cave. So when the relative amount of strontium increases and when the relative amount of carbon-13 increases, this tells you that the conditions were colder and drier. And conversely, if the strontium decreases and the amount of carbon-13 decreases, that's an indication that it's wetter. And this cave record, or this flowstone record, really does show that. It shows that during the MIS 12 glacial period, conditions were drier and colder, and during the MIS 11 C interglacial, it was warmer and wetter. And in fact, there was a hiatus on this flowstone record in the middle of the MIS 12 glaciation, and that's probably an indication that there wasn't water dripping in this cave, possibly because there wasn't enough rainfall, or maybe the top of the cave was frozen because it was so cold. And during the interglacial, this strontium, calcium, and carbon isotope record indicates that there was kind of a two-peak signature in the in the MIS-11C interglacial. One was between 418 and 424,000 years ago, and the other was between 402 and 412,000 years ago. And if you look at the insolation, the orbital theory, it kind of matches that signal. So it seems that in northern Italy, the climate was responding to the changes in the northern hemisphere summer due to the Milankovitch orbital theory. The other thing that they measured was oxygen isotopes, so the relative amount of oxygen 18 to oxygen 16. And of course, if the amount of oxygen 18 increases, it should be an indication that there's a glacial period. But this record, it's kind of not diagnostic of a specific climate signal, and as a result, they didn't really interpret it in terms of climate changes. The main thing of interest with this record is to precisely date the end of the MIS-12 glaciation and the start of the MIS-11C interglaciation. This has been defined before using these oxygen isotope records from the ocean, but the chronology of the marine isotope records generally have been tuned to this Milankovitch orbital theory. And like I said, the Milankovitch orbital theory doesn't really work well with this MIS-11C interglacial. So that means there's a big uncertainty on the chronology of when the transition from the glacial to the interglacial period happened. So they did some statistical methods, and they were able to align this flowstone record with the marine records, and they were able to pinpoint the timing of the start of the interglacial to be about 426,000 years ago. At the end of the paper, they then go into some speculation about the overall climate situation during Marine Isotope Stage 11. And one of the puzzling things that many scientists wonder about is that, because of this contradiction to Milankovitch theory, you look at the sea level reconstructions. And again, these sea level reconstructions are based on these marine isotope records. It seems to suggest that once the interglacial started, the sea level was still quite low compared to present. And basically, it took about 15,000 years for the sea level to get close to the present day sea level. And at its peak, they think that sea level was, quite a bit higher than present during this interglacial because it's so long lived. And their speculation is that because the northern Atlantic region was quite warm and for a very long period of time, that this might have been why the ice sheets were able to retreat, even though the summer intensity was not particularly high. And anyway, for me personally, I said this as a comment in the WHO's presentation that I think there should be more caution to interpret this sea level record because, as I said, this sea level reconstruction is based on these marine isotope records, and the chronology is based on the assumption that Milankovitch theory is what's driving the growth and retreat of the ice sheets. And yeah, that doesn't work in Marine Isotope Stage 11C. So the uncertainty on this reconstruction is going to be quite large. And in my opinion, the collapse of the ice sheets probably happened much earlier than what the sea level reconstruction says. And there's some other evidence which I might talk about when I do a deep dive into Marine Isotope Stage 11C in a future episode. But yeah, this is a very important climatic record, and I was very interested in reading it. So anyway, that is the end of episode 1 of the Raised Beaches podcast. Please tune in next time, where the deep dive will be a deep dive into what is sea level. So see you then.